มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay, good afternoon, everyone, and welcome to Colloquium online seminar series number 14, organized by the Institute for Fundamental Study, Nalesuan University, Thailand. And my name is Linyu. I am Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. For this talk, we have Linyu Peng, a friend of mine from Department of Mechanical Engineering, Keio University, Yokohama, Japan, to talk on a topic, Noether two theorems for differential-difference equations. Let me spend a bit more time to introduce our speaker formally. Okay, Linyu Peng completed his bachelor degree in arts and mathematics from Beijing Institute of Technology, Beijing, China, and then he continued his master degree in mathematics at the same Beijing. After that, he went further for his Ph.D. in mathematics at University of Surrey, United Kingdom. Currently, he is a senior assistant professor at Department of Mechanical Engineering, Keio University, Japan. Okay, his research interest is, of course, integrable system. If there is something else you can add on that. Okay. A talk will be lovely, 40 minutes long. Before I stop during the talk, if you have questions, you can put into the comments. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this screen to our speaker, Linyu Peng. Screen is yours. Okay.
Thank you very much for the invitation and the very kind introduction. So it's my very great honor to give a talk here. So please allow me to share my screen. Can you see my screen?
Yeah, it's coming. Yep.
It is okay?
Yeah, it's okay. Yeah.
Great. Thanks a lot. So thank you again. And so firstly, again, I would like to thank Lin for the very kind invitation. So as Lin mentioned that we are already very old friends. So we met almost 10 years ago when we were both doing our Ph.D. in the UK.
Yeah.
Today, I would like to talk about Noether's theorems for differential-difference equations, also known as semi-discrete equations. And this is a joint work, partially based on joint work with Peter Hydon, who was my Ph.D. supervisor. Okay. Oops, sorry. Okay. And so this paper's content, I would like to firstly give a quick review on symmetry methods, and then for differential equations, that's what I mean. And for differential difference equations, so I would like to give firstly what is the challenge and what we solved, or say what is the method that we used to solve the challenge. and also the extension of the Noether two theorems to the semi-discrete sense. Because many of you are from physics, I suppose, so you know there are two theorems in Noether's original paper, in fact. Okay, so symmetry, so continuous symmetry, that's what I mean. Of course, for symmetries of algebraic equations has been studied even before Sophie's Lee, but for continuous symmetry, I think it was Sophie's Lee firstly studied it. So his motivation was he was wondering that why some differential equations, ordinary differential equations, why some of them can be easily solved, but some of the others cannot be simply solved, or even some of them that we cannot solve them. So it's like the solvability or integrability of all these. And his method was to concede transformations, continuous transformations. And also we know now this is in fact the origin of Lie groups and the algebra. After Lie, so there was a period of time that people were not very much interested in this topic, but people instead, mathematicians, developed the theory, the Lie group and Lie algebra, quite a lot. And another very important work was by Amy Noether, who she was invited by David Hilbert and Felix Klein, two very famous mathematicians, to join Göttingen in 1915. Their motivation was to study Einstein's relativity. That they were interested in the conserved quantities of Einstein's relativity. And in the same year, Amy Noether proved these Noether two theorems in a single paper, but finally published it 3 years later in 1918. Okay, so after some time, so as I said, that people were not very interested in Lie's method in the first several decades, but later this Russian mathematician Ovsyannikov restarted the method and then developed it quite a lot. So in fact, many famous mathematicians in the symmetry group were students of Ovsyannikov or grandchildren of him. And then this also was brought back to the West by George Bloom, and then also developed in all different directions by many famous mathematicians. I couldn't, of course, mention all of them. I only listed quite a few of them. Okay, and for finite difference equation, the study was a bit later. The first paper I knew, the first paper, according to my knowledge, it was by Maeda, who is Japanese. So he published a paper in the 1980s on discrete Hamiltonian systems, and he proved a very special case of Noether theorem for that special type of dynamic system, discrete dynamic system. And then Donald Nissen, Peter Hydon, Elizabeth, and many others, they developed quite a lot on the symmetry methods, conserved quantities, and also, of course, Noether theorem. And for finite difference, for semi-discrete equations, for differential difference equations, of course, we know the very famous example in total lattice is in the 1990s, I think 1991 around that, Detternary and Pavlovitchnis, they were trying to extend symmetry method to differential difference equations. But their method was just simply using the same technique as what we have for differential equations. In fact, later that we know that is not very exact. Okay, there's some more dedicated analysis is needed. And Yaminov, particularly his famous integral systems, in fact, he used symmetry methods to classify integrable differential difference equations. Of course, there are many other people also contributed quite a lot. So as I mentioned, that for differential difference equations, there is a challenge, which is that the non-commutativity. Non-commutativity means that in the semi-discrete case or in the differential difference case, we have the differential with a continuous independent variable. We also have the discrete independent variable. So if a transformation is applied, then they are not commutative, meaning that if you first do differentiation, then do shifts, or you first do shifts and then do differentiation, the results will be different, but this will be very conflicting with the symmetry methods. They must be consistent, otherwise, otherwise you cannot apply the symmetry method. Okay, so Deutscher and Pavard, they also realized this problem, in fact. So they were trying to solve it in a paper published in 2010. Though they used to connect the continuous version with the semi-discrete version, and they proved a new prolongation formula, so a new symmetry prolongation formula for 1 + 1 dimensional differential difference equations. But because it's based on the continual limit, so it's very difficult to say if we change the way of taking limit, the results may be different. Also, if we extend to high dimension cases, it may be also, well, not as easy, also, as the 1 + 1 dimensional case. I was interested in this program, I mean, a bit later, but I was trying to, I was motivated by, in fact, some mechanical systems, the interconnected mechanical systems, as I'm going to show later. But I found, there's some gap between the symmetry methods and in particular, there was no Noether theorem, basically because the symmetry method for differential difference equations was not completed. Okay. And in this paper, so I could prove a spatial case, and finally in paper with Peter Hydon published this year, we could finally totally solve the problem. And that spatial case I introduced in this paper. In fact, it's the only case possible for differential difference equations, which means basically the trilogy for semi-discrete equations is totally solved. Okay. So the motivation, as I said, so for instance, in integral system, total lattice or Taylor equations are semi-discrete equations. Of course, there are also quite a lot of new equations. For instance, people are studying integral semi-discretization of PDEs, for instance. Recently, there are a lot of new equations are coming. But I was particularly motivated by this result. So also this collaboration, this was with my collaborator from Waseda University from Japan, Tokyo. So when we were studying this integral system, we have a lot of ILC circuits and interconnected with each other. In a single circuit, so there's a continuous time, but all of them are interconnected. So there's a discrete independent variable, for instance, if this is 1, 2, 3, and so further. But when we obtained the system, we want to find the conserved quantities. So I was searching the literature if there is a Noether theorem, but in fact there was nothing on it. So that was my motivation. Okay, that was when the research was began. So as I said, I would like to quickly introduce symmetry methods. I think it's very simple. And if you see the word symmetry, so it's something symmetric. So symmetry, in fact, in mathematics, so is a transformation keeping the object invariant, or say unchanged. Though there are discrete symmetries. For instance, if you rotate the equilateral triangle, but in these symmetries, usually we are more interested in continuous symmetries. One reason is because discrete symmetries are usually very difficult to calculate. Okay, and if we think of this unit circle, so you can see that we can rotate it by any angle. From your eye, you cannot distinguish the difference, so which means the object is unchanged. So that's continuous symmetry. And if this is because this is a unit circle, let's think of it as a unit circle, okay, on the plane. So we know that those rotations will be SO2. I mean, with the SO2 group. So we can write it in this way as a transformation, okay, by the SO2 matrix. In particular, so this will be, of course, this is the Lie group, but of course there's the related Lie algebra, that the so-called infinitesimal generator. You can think of it as the tangent vector at the starting point. In fact, in this case, it's isomorphic to the algebra of SO2. Okay, In symmetry methods, or say in symmetry analysis, usually we use the infinitesimal generator rather than the transformation, because sometimes to get an exact form of the transformation can be very difficult, but we can get the Lie algebra easier. Okay. So a symmetry. So here this is an example of a continuous symmetry. So it's a transformation keeping the object environment. From a mathematical point of view, it means that the algebraic equation will look exactly the same. So the original equation and the new equation written the new coordinates, they look exactly the same, but written in different coordinates. Okay. And this idea can be extended to differential equations. But for differential equations, the difference is that we have differentiations. Okay, so we have to prolong. So prolong is the word we use. We have to. So for instance, we have a transformation for x and y. We have to prolong it or to derivatives. Okay. So for instance, take this Riccati equation as an example. So of course, this now the transformation is given, okay, and there's one parameter here. So usually it's called one parameter locally group. Okay, and after using this transformation, if we calculate the differentiation written the new coordinates and of course express everything in the new coordinates, and then we can get that the new equation looks exactly the same as the original equation, but written in the new coordinates. So you see, it is exactly the same, but written in the x2 to y2 coordinates only. But for differential equations, one challenge is this one. So we have to extend, as I said, to prolong the transformation on x and y. For instance, if we have a transformation on x and y, we have to prolong it to derivatives. Okay, here, for instance. For all these is rather simple. So we can use the chain rule. Okay, just to use the chain rule. So this dx is the total derivative. We can simply prolong it to first order derivative, second order derivative, and so forth. So forth. But for partial differential equations, it's a bit difficult because this one, if x is scalar, then this is scalar. But if x is a vector, then this will be the Jacobian matrix, which means that we have to multiply the inverse of the Jacobian matrix. So the calculation can be very messy. So to determine a symmetry, or say to determine symmetries of differential equations, then there's the so-called linearized symmetry condition. There are two approaches, mainly two approaches. One is using Taylor expansion. Another one is using the infinitesimal generator. But this infinitesimal generator also has to be prolonged. Okay, so this is the prolongation of the transformation. After we prolong the transformation, we can prolong the infinitesimal generator. Okay. So now you see it is very important. So the prolongation, or say the prolongation of transformations is very important. So we have to prolong the transformation to derivatives, and it must be consistent. Otherwise, it's not unique. Okay. So this prolongation formula is very important, as we see. To prolong the transformation, you just using the chain rule. But to prolong the infinitesimal generator, it means concede the tangent vector at this point. So because the infinitesimal generator, the component for x and y, so this c and phi, as we defined, is the tangent vector along the x and y direction. So simply the prolongation, so the next term will be the vector field along this next, or say the transformed derivatives. So that definition is very natural, but how to use this c and phi to define this new coefficients, it's a bit challenging, but of course already solved. So the general prolongation formula for the infinitesimal generator. So firstly, if this infinitesimal generator is given, so the prolongation will be totally determined by the v. And usually we write it in a so-called evolutionary representative, which means the independent direction will be c times dx rather than the partial one. Okay, sorry here. So this is the total derivative plus the characteristic function times or say along the dependent variable direction, and everything, or say the prolongation, everything will be determined by the characteristic. Okay, that's why it's called the evolutionary. So everything is determined by this Q. So Q is very important. Okay, and this evolutionary representative, in fact, is essential for the proof of Noether theorem. So, so the challenge for semi-discrete equations, as I said, is the non-commutativity. In this talk, I will just or say let us just focus on the simplest 1+1 dimensional case. So we have one-dimensional discrete independent variable and one-dimensional continuous independent variable. Many examples are in fact 1+1 dimensional. But of course, if you consider space-time, we also have multi-dimensional cases. In our papers, we consider the most general cases. So, well, P plus Q dimension. So you can find the most general results in the papers. So I'm going to use the shorthand notation. So U is the dependent variable. So it's a function of the independent variables, and sub-index will be will mean shifts along the discrete direction, and super indices. So the dash, double dash, or just 1, 2, they mean derivatives. Okay. So the non-commutativity means if we firstly, of course, we assume we have a transformation on the dependent and the independent variables, just as what we have for the continuous equations, differential equations, also for discrete equations, it is the same. Now, the thing is, for shifts and derivative, it's somehow fine, but the thing is, for the dependent variables with both shifts and derivative, then there's a problem that do we firstly shift or firstly differentiate? In fact, from this example, this is a very simple example. It's x tilde with somehow translation along x direction, the u is invariant. In fact, for this simple example, you can see that if we firstly apply, if we firstly apply differentiation, then use shifts, or we firstly use shifts, S means shift, okay, along the discrete variable, or say discrete direction, and then use differentiation, we can get totally different results. Let me see. Right. So it means that they are not, maybe, let me see, maybe I made a typo here. No, not at all. Sorry. I thought there was a typo, but no. So you see, they are not the same because this one is the same, but here it shifts of ux, but here it's ux. So that's the difference between them. So which means that they are not commutative. So if they're not commutative, so what is the definition of U1 dashed? That's very, well, because it's not unique, then there is a problem. So the solution to this non-commutativity, in fact, is regular transformations, okay? Which means that the transformations are, so the transformations along the independent variable, so along the x direction, is independent from the discrete variables. If we write it in the vector field sense, then it means this the coefficient is independent from n and anything related to n, so which means is a function of x only. And I call them regular, and originally Navy, Dutcher Navy and Power Vintage, they call them intrinsic. Okay, and the thing is, we prove that if we wanted to preserve the structure or the geometric structure of semi-discrete equations or differential-difference equations, symmetries must be regular. So that's our result. So why? So it is stronger. So semi-discrete is much stronger. I mean, the geometry is stronger than differential case and also the discrete case. For instance, in discrete case, if you want to preserve geometry, it means the adjacency between 2 points at least should be preserved. So in the semi-discrete case, at 2 discrete points, we have a continuous fiber. So there's parallel fibers at all different discrete points. Okay, so this structure must be preserved, and to preserve this structure, so the symmetries can only be regular. Okay, if the symmetries are regular, or just say consider general symmetries, then we can have a unique definition of the prolongation of transformations. That is very important. And with this unique transformation of the prolongation, that we can define the prolongation of the infinitesimal generator, which is evolutionary. Okay, but of course now evolutionary meaning that it is evolutionary both along the continuous and the discrete direction. Okay, along the discrete continuous direction, then it's a total derivative. Along the discrete direction, then it's shifts. Okay, and Q is still the characteristic. And symmetries of differential difference equations can then be determined by using a similar linearized symmetry condition, or you can use Taylor expansion approach. Both are fine, but it is, I mean, the prolongation of this infinitesimal generator is essential. Okay, without it, we cannot obtain the linearized symmetry condition, or say we cannot apply it at least. Okay. So the proof, in fact, why so? So the proof I didn't put in today's slides. So the proof, in fact, it's given in the paper. So if you're interested in the details, you can find the proof there. It's a bit complicated, though. Okay. So let's see an example. So this is the well-known total lattice. The second order derivative equals the explanation of u minus 1, which means n minus 1, and this is un, and un plus 1. And using our new approach, so we can calculate all easily point symmetries. It's 4-dimensional. So compared with the with the paper, or say with the result of Daicha and Power, in fact, what they obtained was in this form. So in their case, this f is arbitrary. Okay. But in fact, they also realized f is arbitrary. I mean, this is not a symmetry of total lattice. So in the original paper, they tried to exclude this one. Okay, of course, they didn't know why it is not. And they just tried to exclude it, and anyway, so that was the case. So in fact, we know that this is not a symmetry only when f is a constant. In fact, there's a very special case. That's the partitioned differential difference cases, which can admit non-regular symmetries. A partition, it means, for instance, just think of example, your discrete, or say your semi-discrete equation is defined on the points 0, 2, 4, 6, 8, for instance. Okay, those discrete points. This is called partitioned. Of course, it can be also 0, 3, 6, and so on. So this is a partition case. So it's defined on 0, 2. Okay. In the partition case, then we can have non-regular symmetries. So if you look at this one, the coefficient of dx depends on n, and also this one also depends on n. So it's not regular. But this is a very typical case, meaning that your equation can be divided into two parts. For instance, for this equation, it's defined on the even base points and the odd base points. So for instance, it can be defined on 0, 2, 4, and you can also add another piece defined on 1, 3, and so on. So that is the case, in fact. So in some sense, it means that we can, firstly, redefine the discrete variables such that it is not a partitioned differential difference equation. But of course, well, if we just simply discretize some equation, it can appear, of course. This is a general definition of partitioned DDEs, but let's leave it. Because from this example, I think you already see the meaning very well. Okay. So using the symmetries, so besides Noether theorem, in fact, if we have symmetries, we can get analytic solutions using the so-called reduction approach. Or the solution obtained sometimes called similarity solutions, for instance, traveling wave solutions, sometimes called group invariant solutions. Okay, they mean basically the same. So, well, of course, I can't include the details here, but let's see the total lattice again as an example by using the the symmetry. It's 4-dimensional. And we can use the combination of them, or you can use a single one of them. I only considered like 2 examples. If we use the combination of the first one, the fourth one, we can do the reduction, and then we get this special solution of the total lattice, the invariant solution. And if we do in this way, then we can also get another analytic solution. Okay, but this is, I mean, this method is really classic for differential equations. And the Volterra equation is another evolutionary integrable differential-difference equation. So now the difference is that for the total lattice is second-order partial derivative. Sorry, maybe I should say derivative. Now it's first-order derivative. Okay, and U1 is still UN plus 1 and UN minus 1. And all its symmetries can be calculated. So it's two-dimensional Lie point symmetries, and we can use the symmetries to calculate some specific analytic solutions. Okay, but anyway, this is just straightforward. Okay, so as I say that, so now we have the evolutionary representative of the symmetries of the infinitesimal generator, so we can prove Noether theorem very straightforwardly. So we concede a semi-discrete variation problem. This is a functional with summation and with integration, and L is the Lagrangian density function, so-called. And if so, of course, the invariance of this functional, I mean, not only the Lagrangian but the functional, then it's if and only if, say, is equivalent to the so-called divergence, or it's called the infinitesimal variational criterion. So this is the Lagrange density. This is the prolongation of the infinitesimal generator. This divergence of, but now because it's one-dimensional, so it's total derivative. But if it's multidimensional, this is divergence of the Keio multiplied by the Lagrange density function equals to a differential difference divergence. So this is total derivative plus forward shifts. So it's minus identity. Identity is the identity operator. And the continual limit over the step size will be the total derivative. Okay. Okay. So the Euler Lagrange equations, by using variation calculus, we can calculate the Euler Lagrange equations. It is, of course, you can just use the variation calculus, but it's equivalent to using the so-called Euler operator. Now I call it a semi-discrete or differential-difference Euler operator. This minus d is the adjoint of the total derivative, and S shift minus L is the adjoint of the shift operator. Okay, and of course these conservation laws. Now let's assume a conservation law can be written in a characteristic form. So a divergence, so of course now it's a semi-discrete divergence equals to the characteristic times the equation. Now Euler Lagrange equation, but it can be just arbitrary equation, not necessarily to be Euler Lagrange, or say not necessarily to be variational. And this is one-dimensional, so I just write them as multiplication. If it's multidimensional, then this is inner product, okay, with sub-indices and super-indices. So the proof of Noether theorem is very straightforward. As I said, the important thing is the prolongation of the infinitesimal generator, or the prolongation of the transformation. Now it's evolutionary. This is the total derivative part plus the evolutionary part. From the invariance condition, basically it's nothing but integration and summation by parts. In the continuous case, it's nothing but integration by parts. Now it's summation and integration by parts. So here we have the total derivative Keio dl and L d Keio, so we can write them together as d L times Keio. Okay, and here because it's evolutionary, so we can move this total derivative by using integration by parts to move to here. So we can take the q outside. In fact, that's integration by parts and summation by parts, and then we can find the conservation law, which is written in the characteristic form, whose characteristic is Q, but Q is originally the characteristic of the symmetry. So now it becomes the characteristic of the conservation law. So Noether theorem, in some sense, means the one-to-one correspondence between the characteristics of symmetries and conserved quantities or conservation laws. Okay. And of course, this can be generalized to higher order symmetries, or sometimes called generalized symmetries, meaning that now, of course, we only consider Lie point symmetries, but this can be equally generalized. Well, I'm going to skip this. Okay. And in fact, Noether theorem deals with finite dimensional symmetries. That I think is well known to the audience. Of course, because the total lattice is so well known, so I would like to consider the Volterra equation. But the Volterra equation itself, is not variational. Well, if you look at the equation, because all Lagrange equations, if the Lagrangian is non-degenerate, then all Lagrange equations usually are of even order. But here, this equation in first order, we expect somehow is not variational. But if we do a change of variable, to change from the u coordinate to the v coordinate, but it's not a change of coordinate because now it's a non-local because these shifts are included. Okay. So we can obtain the equation, the new equation written in the v coordinate, which will be variational, and the Lagrangian is written this way. And by using some very simple symmetries, variation symmetries, we can get the conservation order, of course, firstly in the v coordinates, and then we use this substitution to move back to the u coordinates. So these two are the conserved quantities or conservation orders of the Volterra equation itself. Okay. But the remark is that a general inverse theory is not yet available, meaning that if an equation is given, how to determine if it is variational or not. So for differential difference equations, this is still somehow open. And the Noether second theorem deals with infinite dimensional symmetries in a sense that the characteristics depend on an arbitrary function, or not necessarily one arbitrary function, but it can be many of them. So for instance, if the characteristic depends on R number of independent arbitrary functions, which means f1, f2, and fr, they are independent from each other. This is usually called the infinity dimensional because functional space is infinite dimensional. Okay. And in this case, in fact, from physics, we know that the gauge symmetries are, in fact, related to Noether's second theorem. And if we have this type of symmetries, then it means the all Lagrange equations are, say, degenerate. So there exists differential. So now, of course, differential-difference relations among the all Lagrange equations. Okay. And this D is a differential differential operator, which means both differentiation and shifts are included. The proof, in fact, is somehow straightforward as well. And let us consider a very simple example. This is of course, there are more interesting examples, for instance, the Young-Mills field or the Higgs mechanics. If you're interested, you can also consider them. In our paper, we considered this very simple example. This is the interaction of a scalar particle with mass m and charge e in an electromagnetic field. So now the space-time is the Minkowski space. So there's the Minkowski metric. We have one-dimensional time and three-dimensional space. So of course they are serving as the independent variables. So so now this is a continuous case. So in the semi-discrete case, we try to discretize time t, okay, and keep the space as continuous. And the dependent variables are there. In fact, in the real sense, they are four-dimensional. Okay, so one is scalar and complex valued size of the wave function. So because it's a complex valued, so it's two-dimensional in the real sense, and the real valued in electromagnetic for potentials, it's four-dimensional. So mu means 0, 1, 2, 3. Okay, and the sub-indices and the super-indices are connected by using the metric, so Minkowski metric. This is the continuous system. So of course, this is already constructed from the real physics. So the Lagrangian is written in this way. F is defined here. This comma mu, of course, meaning partial derivative. Okay. And okay, so this is Einstein summation convention used here. Sorry, Einstein summation convention used here. But also here, there's also a summation, but I neglected the summation sign. This lambda means the total derivative plus I is the imaginary unit times E is charge with A. The orange equations, of course, can be easily calculated because now the dependent variables are 6 dimensional, so we have 6 equations. Okay, 1, 2, and this includes 4 of them. In fact, there are gauge symmetries. So it's somehow like scaling, but it's gauge symmetries because lambda is an arbitrary function on the independent variables, and this lambda is real valued. Okay, if we do this, you can immediately see that this function, the variation problem is invariant, and using the No.14 theorem, then we can get the differential relation on the Lagrange equation. So there are 4 of them. And we are trying to discretize, as I mentioned, the time t. And for the fully discrete counterpart, this was already studied. Also, this was introduced in this paper and later studied by Peter Hydon and Elizabeth Mansfield. They established the Noether theorem for finite difference equations, for fully discrete equations. And they used this as an example. Okay. So now we try to discretize the time t with a time step h. Now the Lagrangian, so this semi-discrete or differential-difference Lagrangian becomes in this way. They look like the same as the continuous version, but the thing is, some notations are different. Okay, so here this triangle, say the Laplacian, is not really the Laplacian, but this notation, the forward difference operator. Also, you can think of it as the discrete version of a total derivative. Okay, this is somehow straightforward, but this part, this lambda 0, is somehow different from the continuous case. This is the counterpart of this total derivative, but this part is a bit different. Okay, if you don't discretize in this way, gauge symmetries will not be preserved. Or of course, there may be other choices. And then the semi-discrete Lagrange equation can be immediately calculated, but this E and the E in the continuous case, the Euler operator, of course, are different. Okay, and still we have gauge symmetries. The gauge symmetries along the psi parts is somehow similar, but on A0 is a bit different. Okay, this is the total shift, or say it's called the forward shift difference operator. Okay. And now this lambda is still an arbitrary function on the independent variables, and it's again real valued. Of course, we firstly must show that this is really a gauge symmetry for the variation, for the semi-discrete variation problem. And after showing that, we can get the differential difference relation of the Euler Lagrange equations. And this is the adjoint operator of the forward difference operator. Adjoint means by using summation by parts. In the continuous case, adjoint means using integration by parts. Okay. So I'd like to summarize up here. So basically, what we solved is somehow an open question about semi-discrete equations. How to prolong a transformation, or say in general, to include both derivatives and shifts for semi-discrete equations. This has been an open question for somehow decades. And we can show that this prolongation will be evolutionary, or say equivalent to an evolutionary representative, which is very important for us to prove the Noether theorem. Okay. And so in fact, there's another thing also included in our paper, that's the so-called 1.5 Noether theorem, or sometimes people call an intermediate theorem. In this case, so for the so let's start to review. So for the first theorem, we consider finite dimensional symmetries. For Noether's second theorem, we consider infinite dimensional symmetries, but the arbitrary functions are independent from each other. For this 1.5 symmetries, or 1.5 theorem, still the symmetries are infinite dimensional. We still have a lot of arbitrary functions, but they are not independent from each other. Those independent functions, those arbitrary functions are connected with, or say some of them are connected by differential or non-differential difference constraints. For instance, the wave equation, in fact, that means such type of symmetries. In this case, we can still obtain some conservation laws. So that's the 1.5 theorem, which is a bit different from both the first and the second theorem. Because from the second theorem, we cannot obtain any conservation laws, but the 1.5 theorem can still give us somehow conservation laws. So as I said, the details and more examples can be found in our papers. So if you are interested, please refer to the papers. So I think I would like to stop here, and thank you very much for the attention.
Okay. Yep. Thank you very much for this very interesting talk. I think, yeah. Let me ask you some couple questions first. Okay.
Sure.
So you start from at the beginning about the motivation, which is actually very interesting because there's something actually related to the physical system, like a circuit that you showed actually. But I'm not really sure that actually from that circuit that could somehow that what kind of conserved quantity or that we looking from this kind of thing, or it that's the motivation.
This okay. So this model, in fact, because we were trying to study the geometry of this type of systems,
Okay.
of course, because I'm mostly from mathematics and a bit from physics, so we were interested in modeling such kind of dynamics. After after modeling, so after we get the system, so what we interested was what are the conserved quantities, and also another two interesting things that we were considering. One is the semi-discrete continuum of such kind of system, and another one is the fully discrete discretization of this semi-discrete system. So when we were trying to do both things, do either the continuum limit or the fully discretization, so we have to evaluate the method, right? For instance, if we discretize the method, so we were trying to understand it from the preservation of conserved quantities. So for instance, energy preservation or what. But the thing is, we must firstly know what are the conserved quantities. So that was why I was very interested in this Noether theorem for semi-discrete equations, basically.
Okay. So if I understand correctly, is that from this kind of circuit, you're going to translate into the a set of equation, right? And then you can solve it by, you can do something with it with your method, right? And then you're looking for the conserved quantity after that. Is that correct?
Yes. We were trying to establish a mathematical model, so equations for this type of systems. Firstly,
Okay.
yeah.
All right. Okay. So then you talk about the order that actually matters for doing discrete and derivative, right?
Yes.
I think, and so yeah, this non-commutativity here. So and then you give us an example. Next slide here. Yeah. Okay. So I'm not sure that I might miss the answer that what is actually the answer for this. So what should we do with this? Should we take which one first actually?
Yeah. So our answer is regular symmetries, or say regular transformations, meaning that they are consistent in the case of regular symmetries. So it doesn't matter if you do differentiation first or shifter first. Finally,
Okay.
so that's how we solve this problem. So if you look at this equation, or say this transformation, I should say, so this part is not consistent, right? So it means that in fact this transformation should be independent from U. So U cannot be included here. Of course, our solution is mostly from a geometric study of the basis, or say the space for discrete for semi-discrete equations. For instance, for continuous equations, we have the jet bundle, right? Jet spaces. So now for semi-discrete equations, we somehow establish a similar geometric structure for semi-discrete equations, and that structure must be preserved after using the transformation.
Okay,
And
I see.
by doing so, that's the non-commutativity problem is solved, because transformations must be regular. So if this case is independent from n and u, because u is implicitly depending on n. So if case is a function of x only, then we don't have this non-commutativity problem.
I see. Okay, I see. All right. Okay, very interesting. And then, well, somehow once you get the symmetry, or the symmetry, you can use that those symmetry to find the solution of your equation as well, right?
Yes, but of
Yeah.
course, I mean, now semi-discrete equations are somehow always the counterparts of partial differential equations, right? Because we have at least one-dimensional continuous independent variable and at least one-dimensional independent discrete variable. So at least we should have two independent variables. So they are somehow in the sense of PDEs. So we cannot, symmetries usually give us spatial analytic solutions of PDEs rather than the general solution. But for ODEs, we can somehow get the general solution. But there is no ODE counterpart for semi-discrete equations, as you see, right?
Okay.
But we can still somehow get spatial analytic solutions. For instance, if you are interested in traveling wave solutions, for instance, you can still.
All right. Okay. And so, well, the a very interesting point is that you also have action. You construct an action, and then you do the variational thing, which should actually, you know that actually I'm working on this kind of thing as well, right? Like a form, Lagrangian form, something like that. And but I believe this is not the same, right? The one that actually you put here, the action here, because you get both a summation and integration there, then, or is that not sure.
It is the same action as in physics. It can also be the same action as in Lagrange multiforms.
Right. Okay.
Yeah, so this LDX, of course, we should also define a discrete basis. Then that will be the Lagrange or say Lagrange form along one direction.
Okay. So in this case, it should be two form, right? Or is that one form?
It's a two form, yes. But because we didn't define the one form in the discrete sense, so I didn't write.
Yeah. Because it's discrete, you cannot put in there. Okay, I see. So
algebraically it's fine, but geometrically maybe not so good.
Yeah, I see. Very interesting. Okay, and then what you're looking for is actually, if you have the Noether theorem, you looking for the conserved quantity that normally called the Noether chart, right?
Right.
Is that the Q that you put there? Is that the Noether chart?
Q is I think it's called somehow called density, isn't it? In physics.
What it says again? Sorry.
Maybe it's called density in physics.
Oh, density.
Isn't it? Yeah. So this Q and this conserved quantity, well, from mathematical point of view, they are connected by the homotopy operators. So it's related to a complex. So, for instance, a one form or two form, something like that.
Okay. I think. Well, I'm not sure, because in physics normally we once we looking for the symmetry, there must be like a conserved quantity that we call Noether chart somehow. But anyway, I think it might be the same.
I think the same. Yeah. At least the equivalent.
Yeah, I think so. Yeah.
Right.
Okay. And so, well, that And then you also extend your idea to the field theory at the very
Yeah,
end, right?
exactly.
The question is that so you choose to discretize the time
Right.
in the field theory, right here yeah. So but actually okay, here in this one, okay,
Yes.
and then you get something new
Yeah.
um, uh, because because at least I see that the get symmetry change, right? The way
Right.
you
Of
do
course,
the
it's a bit modified. Say, yeah.
That is the thing. So my question is that so actually in physics we know that actually when we working in relativity, space and
Right.
time are the same equal footing, right?
Right.
So it doesn't matter. It seems to me it doesn't matter if you choose to discretize the space or you choose to discretize the time. It
Right.
should give you it should give us the same, more or less the same thing. But I'm not
Right.
sure what with this setup. Is that
Right. So,
am I understand correctly?
so
Understand?
because I mean, I'm Peter and I both are not from physics. So in fact, for this example, of course, this is just a simple example. For this example, we can discretize either time or space.
Yes.
If you discretize carefully, you can preserve the gauge symmetries.
Okay.
Discretize carefully, that's important. So here, so discretize this part. Let me see. So this F, we have to discretize it very carefully. In
Okay.
particular, also this part. Although I write it's written like the continuous sense, but when mu is 0, it's replaced by this one. So if you discretize it carefully, then the gauge symmetries will be preserved. And it doesn't matter if you discretize time or space. I think both way you can get gauge symmetry preserving method at least.
I see. That what I'm thinking of actually, because I think well in physics we normally well in relativity well space and time are on the same equal footing. It's
Yes,
more like in the fully discrete system, right?
yes, yes, of
Or
course.
or independent variable are on the same equal footing.
Mm.
It doesn't matter which one you choose to working with anyway.
Yes,
Uh,
exactly. Oh, sorry. So for instance, here, I mean, mu and nu can be from 0 to 3. Of course, they are equally in position.
okay, okay, okay. Very okay. Very very interesting. And then so yep. Okay. I'm not sure. Is there any question from the online audience? I'm not sure.
I can only see my screen, so I have no
Okay,
idea.
I also see your screen. There might be no question actually. Uh,
Okay.
okay, then I think well then I think then would be okay for thing because we spend a bit well a time about hour. Okay, for your talk, and thank you again about this very nice talk, and then yeah, very interesting topic, and then very well close to what I'm working on as well about this Lagrangian multiform, that type of stuff. And then I believe that
Yes,
you may need to talk about this stuff again later.
yes.
Okay.
I know your work with I mean about the multiforms, of course, Lagrange multiforms. Yes, I
Yeah,
mean it's quite relevant and quite interesting, of course.
actually. Okay. Anyway, thank you again for this wonderful talk, and then for spending your time here. And then before we go, for the online audience, please spend your time to complete the survey form for us here, and then we can improve our activity next time. And then, well, see you again for the next if Colloquium number 15 next month. And stay tuned then. Thank you very much. Bye bye.
Thank you very much. Bye bye.